Our next speaker is Professor Tomas Palacios, and he received his PhD from Santa Barbara in 2006, now a professor at MIT, and his research focuses on gallium nitride and graphene. Many awards, the DARPA Young Faculty Award, he's also an IEEE Fellow, and he co-founded Cambridge Electronics to productize gallium nitride, and he'll give his talk on gallium nitride and other extreme materials.
Thank you. Thank you. Great. Thank you for your very kind introduction, and to the organizers for inviting me to be here today in this wonderful event to share our thoughts about the future of semiconductor technology. And I would like to emphasize in the title of my talk, gallium nitride and other extreme materials to reinvent electronics. I would like to emphasize the extreme part of it, in the sense that, as we have heard over the last few talks, electronics is at the right time to be reinvented. We need to find new applications, we are looking for new opportunities, and I think it has never been more exciting time to be working on electronics. But if we want to significantly change electronics and push it for 50 more years, we need new materials, because new materials with extreme properties bring new opportunities. And in my own group, we have chosen to work on two main material systems, nitride semiconductors and graphene and two-dimensional semiconductors. And if you ask me why I'm convinced that these materials are going to change the world, the simplest answer is because they have extreme properties. And I'm convinced that with extreme properties come new opportunities. So in the case of nitride semiconductors, these are the largest semiconductors you can think of. The bandgap of aluminum nitride is 6.2 electron volts. Most of the world call this an insulator. I call it a semiconductor. And gallium nitride, a bandgap of 3.4 electron volts. This largest wide bandgap allows extremely high critical electric fields and excellent mechanical properties that will be useful, as we will see later on. But they have many unique properties. They are extremely piezoelectric materials. They are very polar. The mobility is actually very decent, in the 2,000 centimeters squared per volt per second for a charge density of 10 to the 13 carriers per centimeter square. We have fabricated here at MIT and other places transistors with FT and Fmax of 500 gigahertz. And a very low contact resistance in the 20 ohm micron range. This is for nitrides, and I'll talk a lot about that in just a second. But it's not only about the properties that make nitrides special. The reason why I know that these materials are going to be successful is because they are not alone. They are part of a huge industry today, a $20 billion per year industry, which is the optoelectronics. The optoelectronics industry, which is actually paying for most of the R&D bills to develop these materials and these technologies. So materials alone are not enough. Unique properties alone are not enough. You need a huge industry behind to push things. And the question is, how do you get that industry started? We already have it. It's a $20 billion industry focused on lighting in the world. The second material I'm going to be talking about today is two-dimensional semiconductors. These are the thinnest materials you can think of, made of just one atom thick layers. And they have, again, unique properties. Graphene, for example, the most well-known of these materials, is the strongest and lightest material we know, has the best thermal conductivity, and what I think is very important, a completely unique form factor. I mean, we can get layers of any of these materials that span kilometers in length while keeping extremely good transport properties. That has to be useful for something. extreme variety is something that makes these materials also unique. There are more than 1,000 different few atom thick materials, and we have semiconductors, insulators, superconductors, etc., that bring a completely new array of new physics. The same way that I think gallium nitride will be successful because of the huge industry that is already behind, I'm sure that 2D materials will play a role in future electronics because of one property that I think is extremely important. It's very easy to integrate these 2D materials with state-of-the-art silicon technologies at the back end of the line, thanks to low temperature fabrication. And I'll talk about that in a second. So in the next few minutes, I would like to talk about how I see the future, how do I see computers in year 2030, and how these materials are going to play a role. I think future computers will definitely have silicon, but they will have gallium nitride, and they will have 2D materials for power management, communication, both wireless and optical communication. Maybe in logic, and I'll talk a little bit about that, and of course in hardware accelerators. I won't have time to talk about memory in this talk, though, but there are also interesting opportunities there. But let me tell you why I think these extreme materials will be in the power management of silicon chips in the future. And I want to give all the credit for this to Dimitri. I still remember when he came to my office many years ago. I was just starting at MIT, and he told me, hey, Tomas, I'm putting together this program, the MSD program. And you see, one of the big challenges for silicon technology is power management. The problem is that to keep the power dissipation constant, we need to bring down the voltage that we supply to the chip. As we bring the voltage down, the current increases. And in today's silicon chips, we have more than 50, more than 100 amps going into the chip. And that's a problem for two reasons, he told me. First problem, conduction losses. Any small resistance you have is going to dissipate a lot of heat if you flow 100 amps through there. On top of that, the large majority of the input and output pins in the chip are there just to bring power to the chip. They are not doing anything useful other than bringing the power supply to the chip. So we need a new solution, and maybe he told me gallium nitride can play a role. And indeed, we think this can definitely play a huge role. Thanks to his support and MSD, we were able to develop this concept where, as we see it, future silicon microprocessors here, we have a power distribution network that resembles the power distribution network that we have in the US. We don't bring the electricity to the households at 110 volts all the way from the power supply. We bring it at extremely high voltages, low currents, and it's only locally that we down convert from very high voltages down to the 110 volts that we need for household appliances. And the same thing will happen in microprocessors. So as we see it, the future microprocessors will have the power being introduced at high voltages, let's say 12 volts, and then locally that will be down converted to whatever voltages that you need in the logic, in the memory, in the wireless amplifiers. The challenge here is how to do the power electronics in such a way that is very, very small and doesn't take too much real estate. For that, you need power electronics that can operate at extremely high frequencies in the hundreds of megahertz range. So you need really fast transistors. You need very, very tiny transistors, but that can take very high voltages in the 20 to 30 volts range. And that's exactly where gallium nitride can contribute. Extremely high frequencies, up to 500 gigahertz, extremely high voltages. So we wanted to make these converters made out of gallium nitride power converters at extremely high frequencies. And we worked very hard during the MSD years to develop several prototypes of this, and this is the most recent one, where indeed this idea works. We have the silicon microprocessor, and a gallium nitride chiplet that we connected to the top, and where we got a efficient power conversion from 12 volts down to 1 volt. This is, of course, the very first prototype, but it shows the path. I'm convinced gallium nitride will be in power management. But just in the same way, I'm convinced that gallium nitride will also enable on-chip wireless communication. This is going to change the world at many different levels. And there is a revolution that is coming, which is the 5G revolution. The challenge with 5G is that there is a lot of marketing, and some early releases of 5G have already been announced in countries like Korea and Japan. But what people don't like to talk about is that we don't have the right technology yet to get the full potential of 5G. For a very simple reason. The linearity of transistors is not good enough. Today, we don't have the transistor technology to enable 5G at high frequencies, meaning Ka band. And that's a huge problem, and it's a transistor problem. And it was also Dimitri, the one who put me in the path to try to understand that problem and address it. Let me tell you what the challenge is. So, of course, we make an amplifier, and ideally, we would like to be able to amplify an input signal in a way that we only have that signal, but amplified at the output. The problem is that the real world is very tough, and we introduce the input signal that we want to amplify, and on top of the signal amplified, we end up getting intermodulation products and much higher frequency components, which we don't need. And that's a huge problem that is preventing 5G from happening. So the semiconductor community has been thinking quite a lot about how to fix this problem. And it turns out that the origin of these additional frequency components is in the second derivative of the transconductance. So if you take a transistor, you measure the transconductance, you calculate the second derivative, and you do the math, you'll see that all these additional undesired frequency components are proportional to the second derivative in transconductance. And the problem is that MOSFETs are not very good from the point of view of this second derivative. If you do the calculation, no matter whether you use silicon or gallium nitride or gallium arsenide, you get something like this. Second derivative that reaches a maximum and then has a valley. And this is the cause for the non-linearities. And nobody knew how to fix it until Dimitri and Urjal started to work on this topic. Urjal, now a postdoc in Dimitri's group. And they said, oh, we can do a circuit trick where we basically take multiple transistors and bias them at slightly different voltages. And if we bias these transistors at slightly different voltages, then the second derivative component is going to be shifted with respect to each other. And now we do power combining of these transistors, and this is kind of the circuit, and the linearity improves. And they've been working on this for a number of years with circuit designers in Singapore and so on, and they got a very nice performance. They were able to improve the linearity. And I was listening to their talk, and then I thought, oh, that's great, but too bad that I'm not a circuit designer. I care about devices, so can we implement these at the device level? Can we make a transistor that behaves as many different transistors working in parallel with slightly different performance? And that's how the idea for what we call engineer FinFET transistor came about. We were working on gallium nitride FinFET transistors at that time, and what we noticed was that the threshold voltage of these transistors depends on the width of the fin. So as we made the fin width narrower, the threshold voltage in these devices was more positive. So the idea was, oh, what if we make a fin-fed device in such a way that the width of each fin is different? There will be some fins that are narrower, some fins will be wider. What we get with that is a distribution in the threshold voltage of each individual fin device, and then we connect them all in parallel, because at the end of the day, this is still a single transistor. And this was an idea that was sparked by Dimitri's and Urjal's conversation. And it works, and I don't have time to get into the details, but in the standard device, planar device, the second derivative looks like this, peak and valley. In the engineered fin, is significantly reduced, which, when we measure the linearity in the engineered fin device, we can get up to 10 dBs higher linearity than in planar devices, which is huge. And has started a completely new research direction in gallium nitride transistors focused on engineered fins. And it was all thanks to Dimitri and Urjal's insight. Gallium nitride will be in future microsystems also through optical communication. We heard before a wonderful talk on optical systems. And the missing link was always the light source. And the good news is that gallium nitride today, integrated on a silicon platform, so gallium nitride fabricated on silicon, has really good lasers, really good waveguides, really good modulators, and it's all integrated on a silicon substrate today, and is being fabricated by almost every silicon company is working on gallium nitride for power electronics. So there is a very interesting potential there of using gallium nitride optoelectronics for optical interconnects. Sub-5 nanometer logic. I'm completely biased towards gallium nitride. I don't try to hide it. I love gallium nitride. And when I thought of trying to use gallium nitride for 5 nanometer technology, everyone told me it was crazy, except Dimitri, who said, oh, why don't you look at that? It could be interesting. So I did. And it turns out that gallium nitride has very unique properties for ultimate scaling. And I've tried to summarize them here. So it's a wide bandgap material, so the band-to-band tunneling is negligible. Also, the effective mass of gallium nitride is relatively high. In a 5 nanometer device, it's around 0.3 or 0.4. And that's actually a very good trade-off between leakage current and velocity. And it turns out that that is kind of the optimum effective mass to maximize on current. The permittivity is also the lowest among the most common semiconductors, a permittivity of 9. And that's actually very good to minimize short channel effects. It has extremely large density of states, so it allows extremely low contact resistance. The mean free path is around 14 nanometers. It's not great, but it's longer than the 5 nanometer target that we have. And the nearest valley in gallium nitride is very far apart, more than 1 electron volt. So no inter-valley scattering. And on top of that, gallium nitride is a polar material, so it allows us to have a little bit of additional flexibility in the device design. So we started to play with these devices and run some simulations to benchmark how a hypothetical 5 nanometer gallium nitride device would compare. And it turns out that from the point of view of GIDL, gate-induced drain leakage, basically gallium nitride, because of the large effective mass and a wide bandgap, is extremely low. From the point of view of on resistance, high density of states, high effective mass allows us to have the highest on current for a given off current. The transconductance versus sub-threshold slope is also very interesting from low power as well as high performance devices. And when we put all these into a system and we look at the energy delay product, it turns out that gallium nitride seems to outperform, at least from the point of view of these simulations, any other known semiconductor, which is kind of unexpected. It's intriguing, especially for a semiconductor that is already going to be there in the silicon chip because of power management and because of wireless communication. So it's going to be there for power. We may want to take a look at logic. Another very important component of future silicon microsystems is going to be hardware accelerators. And although I'm crazy for gallium nitride, I'm not going to try to convince you to use gallium nitride there. I think the opportunity for hardware accelerators is two-dimensional materials, because it's very easy to integrate them with the back end of the line of silicon. So you can take state-of-the-art silicon wafer and place on top whatever 2D material you like, graphene, molybdenum disulfide, whatever you need. And then at the end of the back end, you just fabricate whatever devices you need for your hardware accelerators. And we've demonstrated that concept in a few different demos. In this case, we have a graphene infrared photodetector array, 80 by 60 pixels, fabricated on top of a silicon readout chip. And it works. And we've done a similar demo with a graphene-based chemical sensor, and it works. And again, the fact that it's very easy to transfer to state-of-the-art wafer makes everything very straightforward. So to summarize this part of my talk, today we have high-density silicon chips. We also have a very interesting interposer technology. The way I see the future is by adding hardware accelerators based on, among other materials, 2D structures that will have infrared detection, chemical sensors, neuromorphic performance. But on top of that, I want to change this silicon interposer. And instead of a silicon interposer here, I see the future as having a gallium nitride active interposer that shares the back end of the line with silicon. But on top of that, on top of providing the electrical connectivity to the high-density silicon chips, we'll have power management, we'll have RF wireless amplifiers, and we'll have the integrated light sources and waveguides, etc. So that's how I see the microprocessor in 20 years from now or 15 years from now. And I think that's exciting, and I think that's going to make an impact. However, where I see the most excitement for the future of electronics is in the fact that no matter what we do, we are running out of atoms. And sooner or later, we are going to have to stop scaling. Sooner or later, even if we go 3D, we'll have to stop scaling. And I see that as a huge opportunity. And the last 2 minutes, just, let me tell you that, of course, this is not the end of electronics. We just need to change the paradigm. And I can think of 3 different directions. The first one, we have electronics everywhere, but in reality, today, we only have electronics in computers and in the communication system. 95% of the objects around us don't have electronics. Can we change the form factor of electronics to bring it to everything? Can we code the highways with electronics? How can we do that? That's one opportunity. Second opportunity, when I think of how electronics has evolved, this is one of the earliest computers, and we all know how the story is today, really tiny cell phones. I see exactly the same story happening in energy. When I look at power plants today and how energy is transformed at the national level, it reminds me a lot to the early computers. And that's going to be transformed. And it's going to be transformed thanks to extreme materials and thanks to electronics. And if we are able to do that, so can we do with energy what we have done with information for the last 50 or 60 years? If we are able to do it, we are going to change the world. And we can see that here. So this is a plot of how all the energy that is being generated in the US is finally used. This is electricity. And the key thing to remember is that out of all the electricity being generated, only the orange part reaches the final user. Everything else is wasted in transmission. We don't use electricity, we waste electricity. And from time to time we use like 30%. That's what electrical engineering should help us to fix. And the last opportunity, and I'll conclude, is can we push the limits of microsystem scaling? And I don't mean silicon microchips. I mean, can we realize or can we get close to this vision of making a microsystem that is so tiny that we can almost confuse it with a biological cell? So we think that that's an exciting goal. And we are trying to do that. This is one of our first prototypes, and a number of people at MIT and other places has contributed to this. But this is a first prototype with some transistor-based timing circuits, some selectors, chemical sensors, with the size of a cell. And it behaves like a cell. Let me see if I can run the animations quickly enough. It looks like a cell. It's not very smart. Cells are not very smart. But it does some chemical sensing. They move around. They have some communication. And we are just at the beginning. And then the question is, can this be then the way to redefine electronics? So I'm convinced we are at a very exciting time. And with this, I would like to conclude. We are at the beginning of a new era for electronics. On one hand, we should keep pushing computing. And I think there is many opportunities there. But at the same time, we should try to come out with the next big thing. What is going to be even bigger than computing? And I think to change the form factor will help. And to do energy, to do with energy what we've done with information will also help. A multidimensional approach is needed for this. We always need silicon, but extreme materials will bring new properties. System and network level thinking is a must. If we make these tiny cells, they are very stupid. They don't do too much. But if we have thousands of them talking to each other, we may be able to build something useful. We are kind of useful sometimes. And this is the most exciting time for electronics in history. We are about to reinvent it again. I'd like to thank my group and sponsors, but especially I'd like to thank Dimitri. And I really hope you won't go too far, because we need your insight, we need your advice to keep pushing electronics and redefine electronics as you've done many times. Thank you. Thank you.
I guess we have time for maybe one question. I want to kind of give all our speakers a little bit of time, a little bit extra time, because they only had 20 minutes to kind of share their enthusiasm with you. But if there's time for maybe one question. Hank?
Do you see a problem with the the crystallographic structure impurities, defects in gallium nitride?
That's a problem that money is fixing. So the material quality of gallium nitride today is orders of magnitude better than 5 years ago, and in 5 years from now it will be even better.
Okay, one more.
Can you give us the C part of the MOS and GaN for those 5 nanometer transistors? The PMOS, right?
We are working on that, and it's working a lot better than I thought, but not ready to share yet.
Okay. All right, let's
Thank you.
thank Tomas.
Thank you.
Okay, I'll keep track with you.